In this video, we're doing second order and higher order differential equations. So we'll do it in one video, the second order and the higher order. So the first thing, just to remind us about the initial value problem. So the initial value problem, very important. So if we have an nth order initial value problem, we want to solve this differential equation. Now, just recall what a differential equation is. So if I have a derivative equal, say, to x squared plus y squared, what do I want to solve? I'm getting a first order differential equation. I want to solve the function. So I'm given the derivative. I want to solve the function in terms of x. Now we have an nth order differential equation. So as you can see here, nth order differential equation, and it is equal to gx. We want to solve for yx. So that's what we're saying here. We need to find a function yx defined on some interval I, containing the initial value x0 that satisfies the differential equation and the initial conditions. Now, what I'm saying here is we have our differential equation subject to these conditions, and they are called our nth initial conditions. Very important. So I will stress it later what the nth initial conditions are. So if we have a second order differential equation, we will have two initial conditions. So here's our second order. Like I said, we will do the second order and nth order in one. So I will just replace in my second order, in my nth order, I will replace n with 2. So in other words, here I have my second order differential equation. Why second order? Just look carefully here. The highest derivative is of second order. Here, the highest derivative is nth order. So we can also get fourth order. We can get third order or any higher order. And here, like I've just mentioned, my second order differential equation is subject to two conditions. N is 2. So now I have these two initial conditions. In a third order, n is 3, so I will have 3 initial conditions. So if I have a second order, it just means that my solution curve must pass through the initial point always and have a slope y1 at this point. So for now, nth order and second order, very important. So let's compare all the theory for nth order and second order that we need to know. Nth order and second order. So to make it easier, let's just first look at second order. Now, just look what I had here again. Very important. We need to solve this second order differential equations. So, as you can all see here, these are the coefficients of my derivatives. And now, for the existence and uniqueness, those coefficients together with with whatever my differential equation is equal to, any function g of x. So the coefficients together with my g of x must be continuous on the interval they give us. And they're very important, the nth. So in this case, a2x must not be 0. So we can all see that if a2x is 0, this term will fall away and we'll get a first order. So that defeats the point. So the coefficient of the highest order derivative must never be 0, and the coefficients must be continuous on an interval. What does continuous on an interval mean? It must be defined on the specific interval we are working on. So there is our second order differential equation. When we're going to do nth order, so what is important now? So if I go back to my nth order differential equation, let's look at all my coefficients. It's a n x, a n minus 1x, up to a 0x. Now, equivalent to second order, they must all be continuous, and gx must be continuous on the interval I. And like I've just said, for equivalent to second order, a n x, that is the coefficient of the highest order derivative, must not be 0. And this is for all x in the interval. So that is very, very important. Now, if I have an initial point in this interval, then the solution yx of the initial value problem will exist on that interval, and it will be unique. So let's compare that to second order. So that means if I have x equals x0 is any point in the interval I, then the solution, recall what I said, we always want to solve y of x of the initial value problem 1 will exist on the interval and will be unique. So the initial value problem, remember we call it an initial value problem. If our differential equation, let's look at the second order differential equation, is subject to initial conditions. So let's just again recap existence and uniqueness. So when will the solution exist for the initial value problem? If the coefficients and the constant a0x are non-zero and gx is, if a2x is non-zero and all the coefficients are continuous on the interval, and so is gx, continuous defined on the interval. And then if I have an initial point, the solution yx of this initial value problem will exist and is unique. So those conditions very important. Now we will look at what a homogeneous differential equation is. Homogeneous differential equation is when we get that our gx is 0. Nth order homogeneous, our gx is 0. So you can all see here in the initial value problem, we will just replace our gx with 0, and then it will be our homogeneous differential equation. So that is very important for later, because in video 1 and 2, For homogeneous differential equations, we will obviously concentrate on when gx is 0. Now we're getting to a very important part, what this video is all about. So if we have two solutions, so just recall now, I'm trying to solve for yx. Second order differential equation. If I have two solutions to the second order differential equation, so they are both solution, then the linear combination of those two solutions will be again a solution. Just to recall, for those of you who have not yet done your linear combinations, it means that if those two are solutions, y1 and y2, a linear combination means that I times it by an arbitrary constant c1 and c2, and when I add it, those two solutions will be added, will be the linear combination. So let's just recap. y1 is a solution, so that means that a certain constant times y1 will also be a solution. If y2 is a solution, a certain constant times y2 will be a solution. When I add them, that's the linear combination, and that will be a solution again. So let's do the equivalent for an nth order, homogeneous nth order. So if these, say up to k, are solutions of the nth order differential equation, then so will be the linear combination. So that means C1, Y1 will be a solution. C2, Y2 will be a solution. And so is CK, YK. And then when I add them all, that is my linear combination. That will be a solution of my homogeneous nth order differential equation on the interval I. So just to recap, very important for the next two videos will be the nth order homogeneous, so equal to 0, and the second order homogeneous, so also equal to 0. Second order because the highest derivative is 2. So that is very important. Now what we're going to get to is linearly independent solutions. So what we are going to do here for later, we will change this y1 and y2 into functions f1 and f2, just to check whether or not they are linearly dependent or linearly independent. Now, if I have a linear combination, so C1 F1 plus C2 F2 is 0, but not both of my C1, C2, not both of them are equal to 0. So say I get C1 5, C2 3, they're not both 0, then my functions will be linearly dependent. But if I do get, and remember that's only when we have equal to 0, if I have that both of them are 0, then both of my coefficients are 0, then my functions are linearly independent. But more on that later when we do an example. Now, how do we check? Because this can be quite difficult to check this way. So we have a specific function we call the Wronskian of functions. Wronskian of functions. If we do the Wronskian for a second order, what we will do a determinant, a 2 by 2 determinant. And I hope you are all familiar with your determinants. So we'll do a 2 by 2 determinant. But in this case, how do we set up the determinant? We will write the two functions as rows. Because remember, I'm busy with a second order. Second order will have two solutions. So hence F1, F2. What will I write then in the second row? I will find the derivative of F1, so F1 prime. I will find the derivative of F2, F2 prime. Then I will do the determinant of a 2 by 2. I hope you are all familiar with this. But I will do more on it in an example. So remember, this is your determinant. But like I said more on that just now. If that answer is not 0, so the Wronskian, and that's how we indicate that we are doing the Wronskian. If it's not 0, the two functions are linearly independent. So let's go to the equivalent for nth order. So to check if whether our functions are linearly dependent or independent, we write a linear combination of the functions. So C1, F1 plus C2, F2 up to Cn, Fn equal to 0. Now, if all those coefficients are 0, the functions will be linearly independent. If not all of them are 0, so that means there can be lots of 0 solutions, but say C3 is not 0, then they are linearly dependent. That's for nth order. Now, how do we check whether or not they are linearly independent? We will now do the same. We'll do the Wronskian. But now we have n functions. We will write our n functions in the first row. Then we will do F1 prime, F2 prime, Fn prime. So we'll do the first derivative of all of them in the first row. Second derivative, second row, up to, just be careful, not nth derivative, up to the n minus 1 derivative in the final row. So just to recall here, when I did for second order, my second row will have the first order derivatives. So that's very important for the Wronskian. Now, if I do my determinant here and I get that my determinant is not 0, then I know that all my solutions are linearly independent. And we are interested in linearly independence, not dependence. So more on that also later in examples. But if they are linearly independent, if our functions corresponding to our solutions here, y1 and y2, if they are linearly independent, we call y1 and y2 a fundamental set of solutions on our interval. So then there will exist a fundamental set of solutions. And then very important, the general solution then of our second order differential equation will be a linear combination of the two linearly independent solutions. So the equivalent when we do nth order, so if all of these functions are linearly independent, they will be a fundamental set of solutions on the interval. And then for a homogeneous linear nth order differential equation on a specific interval, there will exist a fundamental set of solutions. And the linear combination of the fundamental set of solutions will be our general solutions. But all on this later in the examples, because it's quite a mouthful of theory that you need to study. Now you can see that when we do a second order differential equation, we will need the first order derivatives for our Wronskian. If we have a third order, we'll need up to second order derivatives and so on. Therefore, your derivatives are extremely important, and I advise you before you start doing examples to really study the theory that I've given you just now and also your table of derivatives that I'm giving here. So you're all second years or third years at this stage. You should know your table of derivatives quite well. And then I just want to recap on this. If you have a 2 by 2 matrix, how do we do the determinant of A? So in most textbooks, we denote it by A with the vertical lines. How do we do that? We will cross over. So we will say AD, then we will minus, cross over again, and we will get BC. So that is the determinant of a 2 by 2, very important. Then I advise all of you, I'm not going to do it now. We have quite a lot to do in this video. So for revision, I advise you maybe for 3 by 3, 4 by 4, to revise the determinant, how to do the determinant of those nth order matrices, so that you can do revision on. Now let's start with our examples. The type of questions you can get in a test or exam. Now remember in maths that given is very important. Always check what is given and always check what is asked. Those two things in maths are the most important things to remember, or concepts to remember for a question. Let's see what is given. Now they say the given family of functions is the general solution of the differential equation. So they do it the other way around. They were given us a family of functions that is the general solution. Why a family of functions? Because we have C1 and C2. And it is a family of functions for our second order differential equation. So our second order differential equation. Now this is very important. Why is it second order? Just remember what I said, because the highest derivative is of second order. Secondly, why is it homogeneous differential equation? Why is it an homogeneous differential equation? It's because it is equal. Our differential equation is equal to 0. So very important. Now, they've given us that this is the general solution. But from the theory that I've mentioned before, you know now that the two functions, ex and e to the negative x, those two functions must be linearly independent, because if they're linearly independent, there will be a fundamental set of solutions. That means also that the linear combination of them will be a general solution. So let's just to recap, in a second order differential equation, y1 and y2 must be linearly independent. And how do we check linearly independence? We will check the Wronskian. If they are linearly independent, they are a fundamental set of solutions for our differential equations. Hence, the general solution of our homogeneous differential equation will be a linear combination of the two solutions. So this is extremely important for the section we're doing. So, to check if they're linearly independent, I will do the Wronskian. Wronskian, very important. The Wronskian of the two functions. So, recall that for a 2 by 2, I will have, or for a second order differential equation, I'll have a 2 by 2 determinant. So, I write down my two functions in the first row. In the second row, I do the derivatives. Derivative of e to the x stays e to the x. Derivative of e to the negative x, negative e to the negative x. Now I'm going to do the determinant, which is e to the x, e to the negative x. So I cross over times by negative, and then I cross over and I say minus e to the negative x, e to the negative x, which is now negative 2 e to the x, e to the negative x, and that cannot be 0 for all x in an interval. Why not? Just to recall, our e to the x graph will look like this. E to the negative x will be the reflection in the line y equals x. So in other words, as you can see here, they are not equal to 0. Therefore, the product is not equal to 0. And I know that since the Wronskian is not equal to 0, so look what I've done now, they're linearly independent. Since my Wronskian is not equal to 0, hence the fundamental set, and hence the linear combination will be a general solution. So that's why they told us here that the family of functions will be a general solution. But now they say find a member of a family that is a solution. When we have to find a member of the family, we need, so this is very important, if we need to find a member of the family that is a solution, we need to solve C1 and C2 given the initial conditions. So this is very important. We're going to use the initial conditions and we're going to substitute it into, our general solution. So therefore, if we substitute, so just remember this, a common mistake students make, it was given that y0 is 0. Hence, when x is 0, y is 0. That's why I've replaced x with 0 here, and I make y equal to 0. And by now you should know e to the 0 is 1. So therefore I got my first equation there. Now look what else is given. Secondly, it's given that the derivative at 0 is 1. Also a common mistake, students will first substitute 0 and then do the derivative. No, from first year, you know that we need to do the derivative first, which will be c1 e to the x, and then the derivative of e to the negative x, negative c2 e to the negative x. So that's very important. Like I said, your derivatives. Now they said y dash of 0 is 1. In other words, we're going to substitute x equal to 0 in our derivative and equate it to 1. So we have substituted my x equal to 0, I equate it to 1, so I get my second equation. So I have my two equations, and I'm going to solve them simultaneously. Now remember, two variables, two equations, I solve simultaneously. Now what I prefer to do here, but you don't need to do it, you can do substitution, but I prefer elimination also for later. What does elimination mean? Just like the English word is saying, we eliminate. So if I add equation 1 and 2, can you see here c1 plus c1 is 2c1, but c2 minus c2 is 0, so I'm eliminating c2 first. I get 2c1 is 1, in other words, c1 is a half. Now I can just substitute c1 a half back into one of my equations, but I substituted back into equation 1. I substitute back into equation 1, so I have c1 plus c2 is 0, that's my equation 1. I get a half plus c2 is 0, hence c2 is negative a half. Now what do? I go back to my general solution. I replace c1 and c2, and there I have my one family of solutions of my initial value problem. So this last part, finding c1 and c2, you should all be familiar with that from first year simultaneous equations. Okay, let's get to our example 2. So it's going to get a little bit harder. An exam type or test type question. They ask us determine whether the given set of functions is linearly independent on I. I here will just be all real numbers because minus infinity to infinity, real numbers. So most of the time they will give you an interval just to make sure that your Wronskian, whenever you do Wronskian, it's for all x element of real numbers. Now they have given us the 3 functions. So what do we want to see for later? What is it all about. Now remember, so like I said, this is extremely important. We want to check if the functions are linearly independent by doing a Wronskian. If the Wronskian is not zero, these two functions form a fundamental set of solutions, and therefore the linear combination of the solutions will be a solution of the differential equation. But just make sure here, in this case, we have three solutions. So in other words, we're going to look at something like this. The general solution of our three solutions. So that means we want to check if the linear combination of the three solutions will be a general solution to a third order differential equation. Why third order? Because I have two solutions, or three solutions. Two solutions, third order, and so on. So this is very important. What I'm saying now, dy dx plus a0xy is 0. 0 because we are doing homogeneous differential equations. So, if these three functions, the Wronskian of the three functions not equal to 0, we know that the linear combination of them will be a solution to our third order differential equation. Now let's get straight onto our Wronskian. So, because we have three functions, we need a 3 by 3 determinant. So, very important for our 3 by 3 determinant, just remember that we are going to get for our Wronskian, let me just write it here, for our Wronskian, we will have F1, F2, F3. In the second row, we will have F1 prime, F2 prime, F3 prime, the first derivatives. And then in our third row, we will have the second derivatives, and we will do the determinant of a 3 by 3. So, in other words, what do we need? For each of these functions, we need the first and second derivative. Hence what I said earlier, you really need to know your derivatives, and then also that's why I provided earlier the table of derivatives. Our first function is 5, the first derivative is 0, the second derivative is 0. That's easy. Now our second function is cos squared x. A mistake students often make before they start the derivative, they forget that you have to write your square on the outside for the trig function. This is very important and for all trig functions. So that's a common pitfall, but even for second years, even though you should know it by now. Now we're going to do the first derivative, which is the chain rule. So it's 2 cos x, derivative of cos is negative sine x. Very important. So that is our first derivative. Okay, now we're going to do our second derivative. So what I can do here, I can take the constant out. I have cos x sine x. So the second derivative, I hope you all know the product rule. I will keep cos as it is. Derivative of sine is negative cos I made a mistake there. Derivative of sine is cos x. Then plus derivative of cos is negative sine x and sine x as it is. You should be all familiar with that because that is just the product rule from school, or from first year. So that derivative now, or let's just color code it. That derivative is now what I got here in my first line when I times in. I'll tell you just now what I've done there when I've simplified it. So that is my second derivative for f2. And then I still have an f3, so I'm not going to do everything there to save some time, but my f3 is equal to sine squared x, so the same there, sine x squared. My prime f3 prime will be 2 sine x cos x. So 2 sine x cos x, what I have there. And now I'm not going to do the second derivative. You know now, you can try it by yourself. It's just the product rule, and that is my purple line. Now I just want to show you what I've done here. So these are just all my derivatives. I just want to show you what I've done here. The green part, I have just simplified this. Now you should also know this from first year. So if I simplify this, I get negative 2 cos squared 2 sine squared. Now what is very important, what I do there, what happened there now for my next step, I took negative 2 out and I have cos squared minus sine squared. So I took negative 2 out and I have cos squared minus sine squared, which is negative 2 cos 2x. So I hope you are all familiar with this. So I took negative 2 out. I have cos squared x minus sine squared x. And by now you should know cos squared minus sine squared is cos 2x. So that is very important. Let's look at the purple part. The purple part here, very important. So what did I do? I'm just simplifying that part. So I have 2 cos squared minus 2 sine squared. Take out a 2 cos squared minus sine squared, which is cos 2 cos 2x. So I have just replaced them in here after simplifying. I've just replaced them here. Then, very important, this you should know from also first year. 2 sine x cos x is sine 2x. Hence the minus sine 2x. Minus sine 2x, and 2 sine x cos x is sine 2x. So I've just cleaned up my Wronskian by doing all the simplifying from my basic trick, double angle formula. So very important to know your double angle formula. So let me just add here on our theory sheet that you must please remember cos 2x is cos squared x minus sine squared x. Sine 2x, 2 sine x cos x. So, but hopefully you know your first year trigonometry and derivatives quite well, because you never know what can come up in a sum. So where are we now? We have this Wronskian. So I've just copied it onto here, on here. Now, very important what I said here, and you should all remember this also from first year. I always expand my determinant according to my rows of 0, row of or columns with the most zeros. So I'm going to expand my determinant according to my first column. Why? Since I have 2 zeros in that column. Now, how do we do it again? So please revise your 3 by 3 determinants, but just to go over it quickly, remember your signs. We have a plus there. Then what do I do? How do I do my determinant? I will cross out the row and column my 5 is in, and I will write down whatever is left in a determinant. Now recall from earlier, we have a 2 by 2, so we're going to cross over. So we have minus 2 sine 2x cos 2x, and I cross over again. I have plus 2 sine 2x cos 2x. And very important, what do I see? I have 0. My Wronskian of my 3 functions will be equal to 0 for all x in this interval. Now, if my Wronskian is 0, just to recap, that means that my functions are linearly dependent, and I will not be able to write them as a linear combination. So I will not be able to say that my general solution y is a linear combination of my 3 functions. This will not be true. Very important. Now, to end off with this video, we are just going to do a more difficult exam type question on Wronskian, linear independence, fundamental set. So let's see what this question is saying. What do they give us? They tell us that u and v, we have two functions u and v, and they're not identical to 0, so they're not equal to 0, but they are continuously differentiable. Now, what does continuously differentiable mean? It just means that all the higher order derivatives will be defined for all x in an interval. So all these higher order derivatives, whatever you need, will be defined on an interval. Now the first question they're asking us, remember I said earlier, given is very important. Now we're going to look at asked. So let's make that blue. They want us first to find the derivative of u over v, then express it in terms of the Wronskian of u and v. So a bit of a different question. And remember what I always say, break down your question. So the first part of A is to find this derivative. My first part of the question. So my first part of the question you should all be familiar with. That is the quotient rule of derivatives. So just like I said before, recap your table of derivatives. So when we do the derivative quotient rule, let's just recap this. So it is going to be v squared in my denominator. At the top, it is the derivative of my numerator times by my denominator as is minus my numerator as is times my derivative of my denominator. That order, very important. So there I have my derivative and I've answered the first question. Now the first part of the first question. My second part, now this is very important what they're asking. They ask here to express the derivative that I've just gotten in terms of my Wronskian of u and v. The answer that I've just gotten here in terms of my Wronskian of u and v. So what do we want to do? We want to first get the Wronskian of u and v. Now just recall from what we've just done earlier, Wronskian of two functions. In the first row, you just write down your functions. Your second row, you have your first derivatives. Now you do your determinant, so I cross over. So it's ux v dash x minus vx u dash x, which if I take out a negative will be u dash x vx minus ux v prime x. Now, a slightly more difficult part. They want us to express our answer in terms of our answer in 2. So that means if I have 1 on the left-hand side, on the right-hand side, there must be a Wronskian somewhere. Now, let's see how we're going to get to the Wronskian. So, remember this is my left-hand side. This is all from my equation 1. But what do I see here? If I take out a negative, I will get this part. And what do I see that is? What do I see immediately? That part is, that is my Wronskian. Let me rather take it this way, otherwise it's confusing. There's my 2. What do I see is inside the bracket? It is my 2. It is my Wronskian. But I still have over v squared. So let's see if we've answered the question. We did express the derivative of u over v in terms of the Wronskian of u and v. So to express just means we can have a scalar multiple times whatever they wanted us to express it in terms of. So that is very important. Now for B, they're asking, use your result in A. Whenever in maths, if they ask, use your result, or they say, hence from A, you need to definitely use this result. So this I need to use this part to show what they're asking, and then show that when the Wronskian is not 0 at some x, then u and v are linearly independent. Now remember what I always say, what is the given part? Let's change the given part to green. What is given? When in maths means given, they say the Wronskian at some zero. The Wronskian is not zero. So given part that the Wronskian is not zero. Then what do you need to show? Let's do that in blue. What do we need to show? We need to show that U and V are linearly independent. So that's what we need to show, that they are linearly independent. But we need to use our results in A. That's why I've rewritten my result in A. Use A, because they said use A. Now what am I going to use? Now I'm going to use the given part, that the Wronskian is not zero. So what do you see? What will I do here? So the given is very important, but before I get there, what will I do? I can times by the denominator on both sides, since it's equal and it is not an inequality. So I can remove the denominator. So in other words, I get this. Now, so just to recap what I've done here, I've times by v squared x on both sides so that they can cancel. But that you should be familiar with. That is just school maths. But I do know that students make that mistake often, that they do not know that you can times by the LCD on both sides. So what do I have now? What do I have now? I have that u dash x vx minus ux v dash x is this, because I removed my denominator. But what do I know? If I take out a negative, I will change the signs in my bracket. Now what will I use now? Now I will use what they have given me, that the Wronskian is not zero. But first also I can divide by negative on both sides. So my Wronskian is not zero. So what do I know now? I know that this equation is not zero, which tells me that U and V are linearly independent, and I did end off with what they have asked. So just make 100% sure you do understand every step of this harder, it's a more difficult exam and test type question. So that is the end of our first video on homogeneous differential equations, and here I've given 2 practice problems that you can try by yourself. I will upload later a video with the worked out solutions of all the practice problems. So this is video 2, enter video 1. Video 2, we will continue with the next section of homogeneous differential equations.